guys, welcome back. We are talking about 4.7. This is solar radiation and Earth seasons. Our learning objectives for today are to discuss factors that cause unequal heating of the Earth and describe how the Earth's tilt affects seasonal differences in temperature. So first we're going to talk about something called solar insolation. I've actually used this term quite a bit in class, but you may not have realized it. Solar insolation is just incoming solar radiation. We use this term in this class when really discussing how much actual solar radiation is reaching the surface of our planet and how much is then consumable by producers in order to photosynthesize and determine how much primary productivity can then be accumulated. So that's solar insolation. We care a lot about this mostly because of primary productivity levels. Something important to note though, and you already should know this, is that the Earth is not heated evenly. So even though we have all of this solar insolation, we have the sun, and we receive this distribution of sunlight, there's always light touching some part of our planet at some point. The actual warming doesn't occur evenly, and there are three main causes for this. So first is going to be the angle at which the sun's rays are striking and the surface area in which it's distributed as a result of that angle. Two is going to be the tilt of the planet. And then three is going to be, depending on the type of surface, the differences in albedo for each of those surfaces. And we'll talk about what each of these mean. So first we're going to talk about the angle at which the sun strikes. So you're probably already familiar with the fact that the equator is generally the most perpendicular to the sun. The surface that is the most perpendicular to the sun is going to have the highest concentration of solar radiation per unit area, or what we call the highest amount of insolation or solar insolation. So even though our planet does have a tilt to it, for the most part, sunlight is always hitting either just above or just below or just at the equator the most directly, or at a perfect perpendicular angle. And so that portion of our planet is generally much warmer because it receives a much more concentrated portion of light. Whereas the higher up you go, the amount of solar energy hits at a much different angle. So this actually does a pretty good job. So you can see in this image, they're sort of mimicking the Earth being at this slight angle or this slight tilt. And as a result, the sun is hitting that angle of incidence is what we call it. As we move closer to the poles, is going to be the angle is going to be spread out over a larger surface area. It's going to lower the amount of solar insolation per unit area. So it'll have a lower amount of solar insolation. So even though because it's spread out over a larger distance, the light is less concentrated. So these areas tend to be much cooler temperature-wise. Now, of course, this will change depending on what season we're in, which is what we're going to talk about next. And so just to give you a little bit of perspective. So our Earth sits at a 23.5 degree tilt. So our Earth doesn't sit straight up and down like this. It's slightly tilted. The Earth's axis that's on this 23.5 degree tilt is spinning on its axis. So we spin from west to east. So from the west to the east, and then we go in a circle. It takes about 24 hours for us to spin around our axes once. So to go around all the way, that's about 24 hours or about 1 day. And then to do a full rotation around the sun takes about 365 days. So we're rotating on our axis, but then as we rotate on our axis each day, we're also rotating around the sun. And that's where some of those numbers come from. So this axis that we're at and this axis that we sit on and this tilt on this axis plays a really big role in the relative distribution of light and therefore the relative temperatures of our planet during those times. So I like to start, well, let's see. We'll start here since we're pretty close to the December solstice. The December solstice is also called winter. The December solstice is, well, winter in the northern hemisphere, I suppose. The winter solstice or December solstice is when the northern hemisphere is tilted furthest away from the sun. So this is where we're at, or almost at, when we get to the December mark. It's like December 21st through the 23rd, I think, is technically the solstice day. But it means that we are going to be the furthest away from the sun. We're going to be tilted the furthest away. So this is when we're actually going to have the shortest amount of daylight. So we'll have more dark hours than we will have light hours. And it also means that the southern hemisphere is going to be in their summer months. And the Tropic of Capricorn, which is the line that is just below the equator in the southern hemisphere, that's going to be the point that is receiving the most direct amount of solar insolation. So this will be the point of the planet that is most perpendicular to sunlight and receiving the most direct amount of sunlight. So after the December solstice, follow the direction of the arrows, we hit the March equinox. With the March equinox, much like the September equinox, we're receiving about 50% on each one in each hemisphere. So we're also about equal with 12 hours of daytime and 12 hours of darkness. So we get almost equal amounts in both the hemispheres, and this is when our planet starts to warm up. Our direct amount of solar insolation is now hitting directly at the equator. So instead of being just below the equator at the Tropic of Capricorn, our most direct amount of solar insolation is now hitting at the equator. So it's moved up slightly, which will warm things in the northern hemisphere. Again, as we continue to rotate, then we'll enter into our June solstice. This would be our summer months here in the northern hemisphere. Our planet is going to be tilted in such a way that the northern hemisphere is tilted closer to the sun. And so, or oriented in such a way that the northern hemisphere is receiving more direct solar insolation. So the sunlight will be now hitting at a perfect perpendicular at the Tropic of Cancer, which is the line just north of the equator in the northern hemisphere. So that is where the most direct sunlight is going to be. These are going to be where we have our longest days, meaning we have the longest day of the year where we have the most amount of sunlight hours in a day, and we have the shortest amount of darkness that we'll experience in one 24-hour period. It also means that in the southern hemisphere, this is going to be the opposite. So anything that's happening in the northern hemisphere, the opposite is always happening in the southern hemisphere. And so equinoxes are always spring and fall or autumn, and then solstices always represent summer and winter. So I also like this image. I think it does a pretty good job. This shows, again, the same, I think it's actually a flipped image, yeah. So this one has spring up above and fall below, and this one has fall here and spring above, but that's okay. So you can see here that day and night are roughly equal in length in both the September and March equinoxes. But then in December and in June, you see the Earth tilted either slightly away or slightly closer to the sun. And this is what I mentioned. You get your shortest day of the year here in the northern hemisphere, and you get something called a polar night. So if you go really, really far north, meaning you're all the way in the Arctic, you're going to get 24 hours of darkness. So on that shortest day of the year, when we hit our December solstice, that is when you are going to have a polar night in the Arctic, meaning you will never actually see daylight. And then all of the days following that will slowly get a little bit more daylight and a little bit more daylight. So that might be only like an hour of daylight a day, 2 hours of daylight a day, which is why it's very tough to live up in the Arctic Circle in the wintertime. And then On the flip, however, if you're up in the Arctic Circle during our June solstice, where we have our longest day of the year, where we have the most amount of light, we have actually 24 hours of light up in the Arctic, it will never get dark. And they have that same problem. It's only dark for a very short period of time. You may only get 1 hour of darkness, 2 hours of darkness. So kind of challenging to live in this area if you like to sleep in normal lighting conditions. Okay. And the last thing that affects that contributes to the uneven heating of the Earth is something called albedo. The albedo of a surface is just the percentage of incoming solar energy that it reflects. So if something has a very high albedo, then it's going to reflect a lot of the sun's energy back upward. If something has a very low albedo, then it's going to retain more of that sun's energy or reflect less back out. So generally, things like snow and ice have really high albedos. So if you look at things like sea ice or water or even clouds, these are like a lighter surface usually. They will reflect up to 90% of light back up into the Earth's atmosphere. So these areas tend to be much cooler. Versus something like asphalt or concrete only has a 5 to 10% re-radiation or sending sunlight back up. So you tend to retain a lot of heat, which is why if you're ever, walking through like a giant mall parking lot or something on a really hot day, it's almost always feels hotter as you're walking through the parking lot because it's really just absorbing that solar energy instead of reflecting it back upward. And then you see these various temperatures. So these can also contribute to sort of this unequal heating of the Earth. So areas that have more water or have more ice will just also be cooler for that reason. Okay, I think that's it. If you have questions, we can talk more in class, but I'll see you soon. Thanks.